Hello, everybody, and welcome to another Tuesday Tech Talk. Today we have Michael from Healthfinch, and he's going to talk to us about some maze generation code, as we not to get confused with corn mazes. So, without further ado, take it away.
Well, first, thank you for inviting me. First, confession is most of the algorithms are not new. They're not new to me. They're new to me, but they're not new. And I mostly got them from this book. So this is something like maybe 6 years ago. It's in Ruby, and I code Ruby. Like at Healthfinch, we do Ruby and Clojure. When I decided to do this, I was just interested in mazes and decided that as I worked through it, I was going to do it in Clojure. And I guess one question: how many people here are familiar with Clojure? Okay, are you just toying with it, or do you actually use it at work? Or? Toying. Okay, cool. So that'll give me some context for what I should explain, how much, what folks might know. But this is, and I'm kind of ad-libbing this, so feel free to interrupt me if there's something to focus on, or I have a couple things I'm going to try to cover just in the time. But if people want me to focus on something slightly different, I can switch my focus. But this code is all up on GitHub, on my repo. It's called Maidol. It's just the Japanese word for mazes. And I walk through the different kinds of mazes here. I have a bunch of different approaches. Some are, some of it's just around displaying mazes. The ASCII maze is a particularly useful one when you're testing and you're just trying to say, hey, do I have an algorithm that makes sense? You throw up a quick thing in your terminal and see what you got. But if you're going to share them, there's PNGs. And then there's code to generate different kinds of mazes. Triangle mazes, there's mazes with insets. I even tried to do like a little NetHack display. This is kind of the primitive NetHack, and this is a NetHack corridor, and this is NetHack room. But the room one, I haven't fine-tuned the corners yet. And there's a number of different algorithms. One thing I'll kind of introduce you here is I have a particular workflow. I work in Vim for the most part, and Tmate, or Tmux, sorry. We use Tmate to share, but Tmux, that's what we use at work too, or at least the Tmux part. And this, to me, it allows me to not have to jump in back and forth from mouse to keyboard, etc. But it also helps me, with flow. And let's see. So in the bottom right-hand corner, this is the actual, it's called the REPL. So it's a read eval print loop. It's an interactive development environment, essentially, where you get to run and execute code. And that's how I developed these algorithms, or developed the code. As I was working through these algorithms, was just print it, or do some code. Is it working? I also have unit tests for these. If we look under test, there's tests around pretty much all the functions, but a lot of it was also just in the REPL trying to figure things out. So the basic concept, most of the algorithms, the basic concept is a grid. There's a few that used what I call a forest. So the forest tends to be more like a graph traversal, where a grid really is just using a vector of vectors or a vector of vector of vectors, depending on how many dimensions you have, and then connecting those. And I can generate a grid here, generate a maze, and let's see, where's my, I think I can just do this. Oh no, hold on. Yeah, so this is Clojure, and I made kind of a big maze there. But the thing that was, Clojure is the language I'm most comfortable with at this point. And that's typically where I want to work when I have a choice. Just once you get used to it, some things are really simple, and then I've had to work in Java, for example, for a very long time, and you just get frustrated after a while with all the things that, like, wow, this conceptually is one little thing, but now I've got to code 20 lines and 3 objects just to do it. One of the things about Clojure is you tend to be data-centric. And so you're really just passing data structures around. And a lot of what you're seeing right now is spec, which is a way to kind of define what your structures are going to look like. So we can see that a maze is just, it will have it has a collection of rows in a vector. And this is just specifically 2-dimensional. The grid is the same thing. So the difference really is just that a grid is an empty layout, and a maze has had links developed. One thing to kind of point out over here is if you look at the maze, and the design I went with is I basically poked holes. Like, you start with a grid where nothing is connected, and then you start poking holes in it. And then the algorithms, or most of the algorithms here, the focus is, okay, how do we start poking holes in that grid? There are other approaches, such as kind of northern graph traversal ones, where you're really saying, here are all the nodes that are possible. Have I linked the nodes? So it's a different approach. A lot of this is kind of, just to give it like a quick overview of just Clojure functions for those of you who aren't familiar with them. This is just a function that checks to see if 2 positions are adjacent. It's passed on line 39. You see it's passed 2 arguments, position 1 and position 2. And this is completely maze or grid agnostic. This is just, if you give me 0, 0, 0 and 0, 1, are they adjacent? Now the reason this is broken out is because some of the algorithms allow you to plug in, and you can say, hey, you know what? The concept of adjacent is different in this algorithm. And one thing you can do with that is you can do weave mazes. So you can have a maze that, maybe you've already developed a vertical corridor, and you come up on a different path. You come up and you kind of get to that point just next to the corridor, and like if you just looked at that next one, that's already occupied, so maybe you would stop the algorithm. But then if you adjust your adjacent function, you can actually look at the next cell on the other side and see, oh, actually I'm going to drill a connection to that other one. So breaking out all the functions, it's a natural thing to do in Clojure. And then it also contributes itself to making some of the functions and some of the maze algorithm generate in a slightly more robust way. I will go to. So just the backtracker, the recursive backtracker is probably the most popular maze generation algorithm, just because it tends to produce the most kind of even mazes. So if we look at some of the other mazes here, like the simplest maze generator is a binary tree, but then you see like there's always this long continuous row here and a long continuous row here. And then one step up from that is one called Sidewinder. You always have a long connected row at the end. It's just the way that the algorithm works. You go from top to bottom, and then at the end you just have to connect everything. And there are different, just to do some terminology, all these mazes are what are called perfect mazes. So a perfect maze means that once you've generated the maze, you pick any 2 points in the maze. There is only one path that connects those 2 points, but there is guaranteed to be a path that connects those points. And so one thing you'll notice here is there's no explicit, at least in the way that I've generated things here, there's no explicit start or end point, because if it actually doesn't matter. Like, because they're perfect mazes, you're guaranteed that whatever point you started at and whatever point is your end point, you know that there's exactly one path there. Now there are ways to make more paths or actually cut off things. But typically for the generation algorithms, you're not going to do that up front. You're gonna modify the maze after you've generated to say, hey, you know what? I actually want to be able to get around this maze in more than one way. Yeah, and so the recursive backtracker tends to produce. It has it has a good flow to it. It's kind of one way of saying it. You don't get a lot of like some of the mazes will tend to produce a lot of dead ends. Some mazes produce a lot of like claw marks. I usually call them. And the recursive backtracker tends to be pretty even in the way that it generates a maze that tends to be aesthetically pleasing, and it also is it tends to be twisty. Some of the other algorithms, you have this risk that like you always know that to solve the maze, you start at the top, you go to the bottom, and then you go back, you figure out how to get back up, or something really crazy like that. That's you don't really want in a maze, typically. Although there are different cases for a maze. If you're trying to get a maze to fit a shape, maybe that is what you want. So just yeah, go ahead.
Are there any industrial applications for mazes? I'm just curious what the book mentioned.
The book and my focus was mostly just to play. Just mazes are fun to do. I even actually at one point, part of the reason I really developed the PNG generator was so I could actually print them, so that my daughter, who's when I was doing this, I think she was 6 at the time, and so it was totally fun for me to just print out like a 25 by 25 maze and say, start here, end here, and then she would figure it out. Yeah, other than that, I mean, the main thing I would think of would be like video games. Like but even then, most games are not going to want it to be completely random. But the principles underlying it, could be used for something like that. Like I've thought about maybe trying to do kind of my own little roguelike or NetHack kind of implementation, just using these algorithms or maybe modifying these algorithms in order to build a maze that you have to navigate through or levels you have to navigate through. Yeah. Okay. So most of the code follows in order to create a maze, and this is just right now it's only enforced through convention, but there's a create method that is what you actually use to create a maze, and a little just explanation of clojurisms is this is a multi-arity function. So if on line 32, if you pass it just a grid, it will pick a random position from that grid and create the maze from there. The second, if you pass it 2 arguments, the second argument it would be the starting position. So then it generates the maze, but it uses like a default neighbor function and a default link function. And this exposing the neighbor function, the link function, the select function, it opens it up for saying, hey, you can, like the weave mazes where I can, if I know where the neighbors are, so the neighbor can tell me like, oh, actually, I can actually connect to 2 places away because of the rules of this one. And then the link has to know like, oh, by the way, if they're not immediately adjacent, you have to mark it in a special way to say this is not just to the left or east. I use north, south, east, west. It's not just to the east, it's actually under and to the east.
So every argument's signature has a different body, is that right? So on line 32 you have a signature grid, and then the create, that's actually what it
Yeah, so it
calls itself.
Yeah, it calls itself passing passing in a random position from that grid, which then calls this one, which then calls this one, which then calls this one. Like if you want to just do, just create a grid. Here's a grid, just create a maze. But then if you want to fine tune it, you can pass in all these arguments.
But basically Clojure allowed me to write 2 completely different functions there that do completely different things. And never, it's the syntax is that doesn't enforce that all these signatures do similar things.
Correct. That's, I mean, you are, it's pretty much convention that to do that. And there are ways to kind of, the spec, which it's a complicated topic to go into, can allow you to make sure that you don't do stuff like that. But again, because in Clojure, this is actually a fairly long function for Clojure. Typically in Clojure, your functions are really 3, 4, 5 lines. And multi-arity functions are kind of frowned on. Like, you really should have a good excuse. Like for most this one, I was really just trying to enable the simple case and then expand to the more complex case. But yeah, in general, you don't want multi-arity functions, but it is there. And so the other just construct thing to look through is this a loop? So Clojure was originally designed to run on the JVM, but now it can run on the CLR as well as JavaScript. But so one of the things about, and I don't know if JavaScript has fixed this, but the JVM, you can blow your stack if you have recursive functions. And so the loop operation basically allows you to write recursive functions that will never blow their stack. But then you have to follow a couple conventions. So it's not as elegant as something like a common Lisp or a scheme. Like Scheme, you don't have to worry about blowing your stack. Well, you could still blow a stack in Scheme, but you don't have to use special notation to do a recursive function. Where in Clojure you do, and it's the loop recur. And so basically, at the endpoints of your call stack, you have to call recur in order to call yourself, or you need to return. But if you call recur, you don't have to worry about blowing your stack, because you also have to program it in a way that you're passing your state along. And I mean, one of the things that I really love about Clojure is the data is immutable, and you tend to just pass your state around. You don't, it's not object oriented where you expect the state to be there, and when I'm just going to ask you for the state when I need it, it's like, no, this is the state. I'm done with it. I'm passing it on. Even if it's passing it back to yourself, you pass it all on. You can get around that with optimizations and other things, but that is generally the way that you code. And so okay.
This is still recursive in Scheme, basically.
Yeah. This is tail recursive, tail call optimized, or tail call elimination. For people familiar with those concepts and in other languages. So then, having this loop, you're essentially having and then here, so your arguments in Clojure and then your let bindings as well are always in this is a vector, so it's the square brackets are vectors, and the first argument is essentially the variable, and the second argument is what is going to go in it. Although in here it's just the arguments, like in the function call it's just the arguments, but in the loop, this is it's more like a let binding where you're saying variable and what goes in, what you initialize it with. So like when we start looping of the maze, the first argument is going to be the maze, which when you start is just the grid. It's going to be empty. Your starting position. And then in this case, we keep a stack. And so at some point I want to do a visual of this. But what the stack does in this algorithm is essentially like if you pick a point from here and you just travel, you travel, then you hit an endpoint. And so you'll have kept all these positions, but then once you get to a point where it looks and it says, I can't go here, I can't go to any of these the 4 positions, east, north, south, east, west, because they're already carved. Then you back up the stack until you get to a position that does have an open neighbor. And then in this case, it randomly, you would randomly choose this one. And then you would continue there. So you keep all the remaining stack while you navigate around. And then as long as there is something in the stack, it means there's still an open space somewhere in the grid that hasn't been linked yet. Yeah?
So if it's choosing randomly, there's an awful lot of corridors in there. Is it more heavily weighted towards keeping going in the same direction?
You can't. I do have algorithms that I put together, and I think that's one thing you can do with the neighbor function. You can actually set the neighbor function in such a way that it can say, "Hey, I just came from the east. I want to try to continue. I want a 50% chance that I'm going to go east versus diverging." By default, what this does is it is totally random. It is just. I think what I do, I basically pick. I find out which of my neighbors are open, and then I randomly pick one of the open neighbors. But yeah, that's part of the or actually I think it's the select function on 37. That's the one that allows you to put an additional bias in. And yeah, again, if you want, that's part of why, like this really, this is the meat of what it's doing. But it's made a little bit more complex because I added in all those options to add in bias in certain circumstances. Yeah, and so basically the argument, what's going on? So starting at line 40, you're checking to say, is there anything in the stack? And so this is just a convention in Clojure where you seek stack is basically, is the stack a sequence with something in it? You know, if it's just an empty list or if it's nil, then this will be false. And then in the false case, you jump to line 52, which is okay. We've completed a maze. Now return the maze. Otherwise, we find out what's been unvisited. So this is where we call the empty neighbor function. We pass the maze in. We pass the function for how do we figure out a neighbor from there. And we pass our current position. We checked, and again we check to make sure that there's something unvisited. So if there is a neighbor that's unvisited, we select one of those, and that select function is where you could be weighted. And then we create a link. And so this recur function is basically calling loop with those three arguments. And so line 45 is the maze argument, line 46 is the position argument, and line 47 is the stack argument. So conj basically says, take this stack that we're building and put a new item on. The link function actually goes and modifies the maze, but it actually doesn't modify the existing maze. It returns a new maze because all the data is immutable. And it just goes and finds the position and the neighbor, and it connects it makes mutual links. So if you have a link to the east from one position, then the next position will have a link west. So it allows for having the links both ways makes generating an output of a maze easier to do. Otherwise, you would have to generate the output in the same way that you construct it. Yeah, and then the next position that you will navigate from is the neighbor. Yeah, and then if there isn't any neighbors to visit, you basically say, okay, the maze I've got right now is fine. Just keep it. Then what second stack does is basically says that top item in the stack was me. I don't want to run this step again on myself. I need to go back one in the step. I need to go one deeper in the stack, and then the rest stack basically says, pop the top off the stack and pass it on. And then this is just a completely recursive algorithm. Ironically, it's called recursive backtracker, but in Ruby it's not recursive. Like when I was reading this, I read the algorithm, I typed it up, and then I was like, I read the description first, I typed it up, and then I read the Ruby code and was like, oh wait, he didn't even write it recursively, because in Ruby it's a bigger risk because you can blow your stack. I think you had a question?
The second function tails the stack, and then the rest function is basically
Yeah. So the second function is, first would get you the first item in a sequence. The second is just going to get you the second item in there. So it's not the second and everything else.
The next argument is the current position, which is the second item in the stack, effectively.
Yeah.
And then you want to backtrack, so effectively rest stack pops
Yeah.
the stack, yielding a new stack without the top item.
Exactly. Yeah, and so when you call it that way, essentially the argument for position is also going to be the head of the stack when you get that call. Yeah.
When it recalls itself.
Yeah.
But it's true too for line 47, right? So actually the head of the stack argument and the pulse argument are always the same. First of stack and pulse, are they always the same?
God, I'm trying to remember if I felt like there was a reason why I didn't just use the top of the stack. I think it was because of starting or something. Yeah, I think just to start off.
Even though it starts off line 39 with list of pulse, which again would make you think that it starts off with a stack made out of just a...
Yeah. It's probably what. Yeah. I mean, and that's the other nice thing about Clojure. Like I literally could, stop this. I have the position already. Well, actually, okay. So what I would have to do here is I'd have to hold on. In here, I would. Sorry. I'm going to want to add an argument here, position, and do that first stack.
It's fine, you don't have to like it.
Yeah, but no, it's actually kind of just, it shows you, it can show a little bit of the power here where we can inject that create over here, I think, and, oh, sorry, yeah, stuff is namespace, that's why.
You also have your specs up there. Will they be the specs that you wrote in line 20 and such?
So those are actually separate. They don't have. I chose to put them right above the function, but depending on how you organize your project, they can exist in separate files. I just happen to put them on top because that was how I wanted to play with it.
But now some of those specs are no longer going to work, right?
Yeah. So
The whole name, the whole calling on an area function might no longer work now.
yeah, actually no, it is good. It will work because the second argument you still need to pass in the position. So I haven't changed the arguments to these can be thought of. These are the public interface, and then all I've changed here is the inner loop. So I actually if I I could, potentially. Let me. I could test the tests for. Oh, sorry, this is a backtracker. Backtracker. I mean, this shouldn't fail because there's arguments, but maybe I'm.
Line 46 is still referenced.
Oh yes, you're right. Thank you.
Still calling curve PRs.
Yeah.
It's just reading out the stack code.
We're going for it now. Looks like.
Ah, come on. Yeah, so everything passed. And so probably now if I just go ahead and inject this code back over. Oh. So yeah, now we should be able to create. Yeah, and I've created a completely new maze. So yeah, it's hard to prove it because I put so much in there, but yeah. Yeah, and that's one of the, and there are other some people set up their environments in such a way that you don't actually see the code fly by. It usually doesn't bother me, but again, this is one of the longer functions. If you have a really long function, I could see why you wouldn't want it to go by, but yeah. So here we just did a REPL debug session, and we've changed the code. Like I can literally just delete that stuff. Cool. And I guess we're kind of at time, right? I can show other stuff if people are interested. And like I said, this repo is public. So if people are interested in this, and it's based on a book, you'd have to buy the book. But yeah, there's a lot of stuff there.
As you move from sort of Java and OO design to functional programming, do you find yourself wanting anything close to an object in terms of a related set of functions on the same data type? So, is there a standard way to do it?
Yeah, you have polymorphic types in Clojure. It's just it's done in a different way. So because underlying, at least with standard Clojure, as opposed to Clojure script, which runs on JavaScript, and I'm sure it's there too, you have ways to basically create objects if you need to. But then you also have what are called protocols, which basically say, hey, if you see this kind of thing, this is what you call on it. But otherwise, and you can do that based on type. You can do it based upon data arguments. You have a lot of flexibility there. And when you do want some of the features, there are definitely positive features to object-oriented programming that, it doesn't throw out everything. And of course, a lot of the early, before Java and C++, my understanding is the most popular object-oriented system was in Common Lisp, which, it's just another Lisp. And you have that kind of stuff available. Is there someone who was over here had a question too? Or,
I was going to ask, because you showed us the backtracker and how the different mazes have different outputs.
Mhm.
Which one's potentially the most complex, or which one do you think is the most enjoyable?
Most of them were pretty fun. When you get into the forest ones, those are also interesting. It's graph traversal, and I literally just even go ahead and use the name because they're developed like graphs. The other one that was kind of particularly interesting, I think is it Prims? Oh, Growing Tree, I think is the one that'll. If I remember right, Growing Tree is the one. Oh, sorry. So this one, and here's another one where it gets kind of heavy. Partly because these are comments. This one got complicated because it's kind of the most flexible. Like you literally pass in everything, and so it's kind of that way that like you've ever done like the Y Combinator, for example. Like if you ever do Little Lisper, like at the end you develop the Y Combinator, which is this function that like when you read it, it just looks so amazingly simple, but it is actually really complicated. Like getting there is complicated, but then it ends up, once you realize what's going on, it's like, wow, this is really elegant. This kind of starts heading in that direction where, the way that it's calling itself and the way that you have to conceive of like, how do you start? How do you determine your edges and stuff? This one to me is also kind of gets interesting in that way. Yeah. Mm-hmm.
There was a lot of TDD, and talk a little bit about spec and how it fits in between. You have unit tests as well, between the tests and static typing.
Yeah. So typical workflow in Clojure is you're going to explore things out in the REPL first. There are tools to kind of take what you've done in the REPL and convert them into tests. But there's it's the testing framework provides all the kind of things you expect from a testing framework. And then spec. So what I have here doesn't actually use the spec at this point. But what spec provides is you can actually do data generation, so generative testing. So you can define your types, and let's go to like grid. Yeah, this is the init grid function. And this is how you say you could take 2 or 3 arguments. So you can kind of, here's how you can define, okay, rows has to be a positive integer, and the columns has to be a positive integer. Like you can't create a maze that's 0 by 0 or -5 by, like it's just, conceptually these algorithms are not designed to handle that. I mean, and technically you can't, like I probably should change this to not just be positive. I should say, hey, you have to at least be 2 by 2, or maybe even 2 by 3. Because is it really a maze if all you got is a grid with like one line? But yeah, the spec, because you define these types, you can do generative testing that will basically say, okay, you've said that as long as I pass you, like in this case, I mean, this is really simple. But it's as long as you pass me 2 positive integers, I will generate a grid. And then the grid is defined above, but the grid is basically, I'm going to be a vector of vectors in this case. And this is a fairly simple example. But then, there's other ones. Oh yeah, like line 99. So here, this is the pos2 function. So this is actually the position 2. So what I want to do is say, give me, let me make sure you give me a direction, north, south, east, or west, and a position, and I give you, like, so you give me a position, and I'll give you the position to the north, or to the south, east, or west. And so you can also do a validation function here that says, hey, you know what, no matter what you give me, whatever you return should also pass the adjacent function. And so it'll generate, and it'll make sure, like, oh, if you give me 0, 1 and 0, 3, they're not adjacent. I can't tell you what the direction excuse me, from those, and I can't return a valid thing. It should like in this case it'll return nil. Yeah. Cool. Yeah.
And what size of a grid or a maze does it take a very long time to generate it? Like, how big have you tried?
Well, my daughter's. Well, the problem then becomes like, how much you can fit on a piece of paper. Do I still have? Oh, I don't have any here, I think. Oh no, so let me go into image. So this is not the biggest maze I've generated, but this is one maze I've generated, and this took seconds. It wasn't. Excuse me. It didn't take that long to make. It's just, of course, printing that out. Like this one, I think you could still print and maybe still like draw a line. But like once you start getting bigger than this, then you either have to do it online or you have to find a bigger printer or something. Yeah, at some point, and each algorithm has certain speed characteristics. Like there's some that are really sloppy around how they find the next open cell, and they do a lot of extra work. The recursive backtracker is nice because it doesn't do that as much extra work as some of the other ones do. So it tends to be that nice balance of like random and like speed and memory usage. Yeah, and yeah, I've made some complicated mazes. I think actually at my LinkedIn profile, I made a maze that was my name, or around the letters of my name, and then I made it like the background image. And that one's, I think, maybe more complicated than this, because I was, I basically looked up, okay, what's the image size for LinkedIn, and then I generated a little graph to how to do it, and it was like, okay. Yep. Cool. All right. Well, thank you, everyone, and.